saw, but the actual process of doing this is going to be a little bit different. So now with the carbohydrate, let's see. I'll scroll up, so I'll cover up that reaction, but this gives us a little more space, and we'll see if we need to see it again. So let's do this in a couple of steps. And the first time we do this, it might seem quite confusing, but then hopefully it'll be better after once or twice. So let's start with a Fischer projection, and we'll stick with glucose. So we're going to redraw glucose again. And now what we need to do is we need to get this into a conformation so that we can form our hemiacetal. We would end up having here on the top, I'm showing this as a carbon. I'll keep this as a carbon for the first one, and then we'll have it disappear into the line. So this is 1, 2, 3, 4, 5 carbons. And then remember back from the first semester of organic that 5 and 6 membered rings are the most commonly found, they're the most stable rings. 3 and 4, you have ring and torsional strain, and beyond 5, 7, 8, 9, so then you have an entropic unfavorable contribution, but 5 and 6 has that balance energetically between the chair conformation, especially for the 6-membered rings, that you can relieve those unfavorable interactions. And so our 6th group here, actually, to form the hemiacetal, is going to be this oxygen here on the right that I just put the little 6 next to, this one right over here. So now we need to get these groups in an arrangement so that we can form that cyclic hemiacetal. And I imagine that this whole Fischer projection is kind of falling over to the right. It's kind of like the Leaning Tower of Pisa, perhaps, that's going to be sitting up and down here, and then it's going to just fall down to the right and has to bounce a little bit. What that means is if it falls over to the right, is that an OH group that is pointing right here will equal down, and an OH group that is pointing up will, I'm sorry, it's confusing, about left. Just pointing to the left is up. So this hydroxyl group here, this first one, is pointing to the right. So when this whole Fischer projection falls over, it's going to be pointing down. This hydroxyl group here, the next one down on carbon 3, that's pointing to the left. So when the whole Fischer projection falls down, that's going to be pointing up. So what we're going to do is have this Fischer projection fall down, but at the same time, we're going to bend it just a little bit. So let's draw the structure and then see if this makes sense. So we have this carbonyl group, line straight. So we're going to have a thing fall down. So we have a carbonyl group. I'll get rid of the C, And now we have, let's put the numbers in here for what we have so far. So this was our carbon 1. So it's carbon 2. So it's going to be carbon 3. Carbon 2 is pointing to the right. And so when the Fischer projection tilts and falls down, that hydroxyl group is going to be pointing down. Carbon 3, the hydroxyl group was to the left. That hydroxyl group is going to be pointing up. Let's make the rest of our sugar. We want to get it into what's going to be looking like a 6-membered ring. So we're going to draw something like this. So this is 3. We have 4, 5. I want to get the number out of the way here. Let's put in our hydroxyl groups. 4 is pointing, highlighted here, 4 is pointing to the right. So it's going to be down. We're at it, 5 is pointing to the right. So that's also going to be down. And then we have to deal with the CH2OH, which I'll just put over here. I want to make this line a little bit shorter. We'll fill in this last hydrogen because that's going to be important. I'm not showing all the other hydrogens. So where we're at so far, we had this Fischer projection fall over to the right. Any hydroxyl group that was pointing down, I'm sorry, I misspoke. Any hydroxyl group that's pointing to the right is now down. and then to the left is up. Now here's a somewhat subtle thing that we need to do, is that we want this hydroxyl group here on carbon 5, which is actually going to be 6 in the ring, actually in the place of where the CH2OH is. So that way, if this hydroxyl group were actually here, it could then attack and it would close our ring out. Otherwise, we'd be going to carrying out some sort of like a mental twist, as having this hydroxyl group attacking and rotating around this carbon. So let's just do this stepwise. So what we're going to do is, let's use a different color, blue. I'm going to rotate around this carbon here. Those are sp3 hybridized carbons, so we can rotate. So like a little loop-de-loop thing to show that we're rotating. And let's see what we end up getting. So first of all of this stuff stays the same. So down, up, down. And now what I've done is I'm going to just actually erase everything and draw it larger. Same thing if you already drew it. Down, up, down. And all I've done with that little blue loop is I'm rotating. I guess you can't see me swinging around my hands, but what I'm doing now is I'm putting the OH group here. So bringing the OH group up here, CH2, OH is in the back, and then this H is down. So this actually looks now like it's ready to be in a structure of the cyclic hemiacetal. And so that we don't have to redraw this time and time again. Well, actually, no, let's just go ahead and do this. We'll redraw it again. So let's have this structure now in the presence of acid. We'll see that this is how the reaction occurs. We're now mixing in a little bit of chemistry with the conformation. We could protonate this carbonyl group. And let's go through the trouble of redrawing everything. Scroll up a bit. Let's just redraw the whole thing. All we've done is protonated here. That's the only difference. All the same. And now we're poised to actually have the chemical reaction where this hydroxyl group is going to attack intramolecularly to form a new bond between that oxygen, this oxygen here, which is oxygen 6, and this carbon here. So that's going to end up forming starting here at the carbonyl carbon 1, 2, 3, 4, 5, 6-membered ring, just like what we had before with our non-carbohydrate. So let's go down since there's more room. So now we formed a ring. All of this stuff stays the same. And now a little bit of a complication, and we'll cover this in a second. We have this hydroxyl group that we have to deal with here. I'm just going to put it drawn like this. And then we have a hydrogen as well, with this hydrogen here. This oxygen still had a proton on it, so it has a positive formal charge. And now we need to do one more thing, is we'll have our acid be regenerated, which is going to take this proton off. And we'll go to the left. Now that's going to form our final product. And before I draw in that last hydroxyl group, notice here, this carbon now, that was this sp2 hybridized carbon of the aldehyde, actually now has an OH group, a hydrogen, this stuff here, and an oxygen attached to it, connected to a carbon. So this carbon now actually becomes chiral. So maybe we'll use a different color. Which in this Hayworth projection then means that that hydroxyl group could be pointing up, the hydrogen, pointing down, or you can get the other stereoisomer. Let me try that one more time, see if we can get a little bit better. No, it's not. Everything here is the same. The only difference is that here, the hydroxyl group is up. Here, that hydroxyl group is down.